note for me, and I will be golden. So we left off, the recorder's going, we left off with effect sizes. And so like alpha, all things being equal, power increases as our effect size values increase. And the sort of the intuition behind that, the logic, if you will, behind that is it is just more difficult in a consistent way to reliably detect small effect sizes because it doesn't take much noise in your data to drown out a small effect size. Where if we have large effect sizes and you have a reasonable amount of noise in your data, noise being air in your data, if you have a large effect size and a small amount of air, that effect size will probably still show. But with small effect size and a small amount of air or moderate amount of air, you're just not going to be able to detect that consistently. And so that's the intuition around effect sizes, or why effect size does have that impact on statistical power. And just a quick primer on effect sizes for those of you, and I think I have a couple slides here that pulls some of the stuff from the Cohen article so that we sort of have this, and some of this will be useful for us as we work our way throughout the semester. So the effect size describes how large the relationship is between two variables. It could be between a set of variables or two sets of variables as well. But in this case, I'm just saying it describes how large the relationship is between two variables. Cohen says the effect size is the degree to which the null is believed to be false, right? That would be another way of thinking about what is effect size. Another way to think about the effect size, it assesses the amount of total variance in the dependent variable that is predictable from knowledge of the levels of the independent variables, and that comes from your textbook. Does that make sense? And then finally, statistical significance examines the reliability of the association, and effect size measures the magnitude of that association. So a test of statistical significance is about reliability, or another way to think about reliability, I think, would be consistency, where effect size is dealing with the magnitude of an association. Again, from your textbook. Some would say, and maybe particularly an older generation of social scientists, a generation, maybe some of the people that trained me, maybe some of your advisors, mentors, there was just nothing more important than, that's what social science is all about, is effect size and finding and maximizing our understanding of some phenomena. And so the goal really is to have these, to be able to construct experiments, have survey data where we can explain a lot of the variability. And my advisor used to say, this is true fact, that happiness is variance explained. Another way to interpret that is happiness is effect size. And so it's just that idea that the more of some dependent variable that we can explain, I don't know, it wouldn't make me, I mean, I guess maybe I'd be a little happier if I explained none of it or close to none of it. But it's just sort of but I think there's maybe an evolving or a more nuanced understanding with newer generations of social scientists that are being trained where the fixation is less about only that sort of brute force, how much of the variability of some dependent variable can you explain with an independent variable. There are other more nuanced ways to understand phenomena, and we might be interested in looking at things like structural equation modeling, where we're looking at, we might try to model some phenomena more broadly, or other network analysis would be another way where we're really not looking at effect sizes, but we're looking at sort of how networks, those of you that have looked at network analysis, how networks might work. So, and I sort of see myself as probably bridging the generation of people that trained me and maybe your advisor and some of you all, or some of the younger academics in the department, where this isn't the effect size isn't the end all and be all. There are other things that are perhaps equally important. And so a couple common effect sizes. R square is by far the most popular. You've probably seen that when you have looked at and read research articles. Eta square is, if you do, or partial eta square would be a variation of eta square. If you do ANOVA or MANOVA, or any analysis of variance, you would be working with eta square. D is less common in communication, but more common in psychology. And so I don't know the last time I picked up a COM journal article and saw that the researchers reported an effect size of D. But if you read psychology, you see it a lot. And it's used a lot in experiments. And it's a very easy calculation. It's a measure of how many standard deviation units the control group is from the experimental group. So it's a measure of, in standard deviation units, how far is, again, the control from the experimental group. And so not all that important for our purposes here, because we won't use it in any of the, we'll use R squared and eta squared. So one thing that I think is really important for us to commit to memory is when we talk about effect sizes, what's small, what's medium, and what's large. And this is what Cohen says. And you can look at the article that you read for today. Cohen says an R square of about 0.01 is small. And an R square of 0.09 would be medium, and 0.25 or higher, Cohen would say would be a large effect size. And so it is. I think it's useful. And this is R squared, not R, right? And so just keep that in mind. And if somebody's presenting R, just make sure that you take the square root of these if you're going to do that. So I think it's useful to keep 0.01, 0.09, 0.25 somewhere top of mind as you read research. And if somebody does a study and they report an R square of 0.01, you can sort of say, well, that's a small effect size. That doesn't mean it's not useful. That doesn't mean it's not meaningful. But if we were sort of to characterize that, we would say that's small. And then, if it's in somewhere around 0.10 or thereabouts, 0.09, well, that's a fairly meaningful, that's a moderate size effect. And then if somebody is reporting R square 0.25 or thereabouts or larger, that's a meaningful. There's that Cohen would say that that's large. And on the next slide, I give a little bit of logic in terms of how we came up with the small, medium, and large. But questions so far? Comments? Good? Makes sense? And so Cohen says this about small, medium, large. And so starting with medium, his intent was that a medium effect size represents an effect that is likely to be visible by the naked eye of a careful observer. So something that has an effect size, the relationship between some independent and some dependent variable that's in that range of R square is 0.09, that would probably be something that if somebody just observed communication, if that's what we're studying, and I assume that's what would be the case, if somebody observed that communication and they were careful and they knew what they were looking for, they probably would be able to detect that. Maybe not in all cases, but in some cases, and that's his quote for sure. And so Cohen notes that a medium effect size is the average effect size across various fields. And so we could easily do this, and if you ever got bored, I'd be happy to help you. We could go out and collect a random sample of 1,000 communication, or 500, or 10,000, whatever you want, and then we could go and calculate their effect size and put it all in the same, so it's all going to either be R squared or R or D. We'd convert them all to a common metric, and then we could just take an average, right? And Cohen says if we did that, R squared should be around 0.09, which is the medium value. And that, to me, that makes a lot of sense. And as somebody who's read a lot of literature in communication over the years, that doesn't seem unreasonable to me. And I'll let you sort of put that to the test over your career to see if you think he was onto something. And so that's medium, which is what again? In terms of R squared equals 0.09, right? And small is R squared equals 0.01, yep. And so we're explaining 1% of the variance, right? That's small, right? It seems too small. Is that all? Can't you do any better than that? Sometimes we can, right? And so, but it is small, right? And just because it's small doesn't mean it's insignificant or not meaningful. It just means that it's small, and sometimes small is all we can do, maybe given a particular research context. He said he set small, again quoting Cohen, he set small effect size to be noticeably smaller than medium, but not so small as to be trivial. And I think parenthetically down here I add, if we were to do this study where we collect 1,000 effect sizes from different journal articles, we would be able to calculate a mean, right? And that we'd also be able to calculate a standard deviation, right? How spread, where's the central tendency, and how spread out are those effect sizes? And I would say that small is a standard deviation below medium. Just like large, this would be my hypothesis. Large would be a standard deviation above the 0.09, the center point. And so, does it make sense? So really, I think useful for us to keep in mind when we start doing multiple regression, and you start doing multiple regression, I'll say, well, there's the R square, is that small, medium, or large? And then you'll have to either pick up this note or have, what was it? 0.01, 0.09 is what? 0.25, you guys got it? Yep. So have that somewhere that you can access. So looks similar. Same test that we did with the alpha. It's just in this case we hold everything constant, but the effect size. In this case, the effect size is d. You could easily convert that to, r squared if you want to. And so this would be colon small, medium, and large. That doesn't look like it rises very much after we get. It's not a straight line. It does rise because again it's asymptotic in that it just gets closer and closer and closer to 1. It never actually is 1. Again, it might round. SPSS might tell you it's 1 because it's rounding to 8 decimal places, but it just approaches 1. And so sort of the similar, a lot of gains if we go from small or something below small to something around medium, but we don't get a lot of power as we go from medium to large. There's just not a lot of gains in terms of power, because this is obviously it's not a linear relationship. It's log linear. So far so good. So we can increase our power by increasing alpha, right? We can increase our power. Is that easy to do? Easy to do, but practically not very useful, right? Because you're constrained by just the academy and what we are needing to do to publish. And so then we can also increase our power by effect sizes. Is that easier to do? Easy to do? Would we be doing everything we could do there already if we probably would be? So it's not something that we have no control over, but we're somewhat limited there in terms of if some relationship that you're interested in has the effect size is small, and that's just the size of the relationship that you find. We could think about, well, let's replicate that study and see if we can get rid of some of the noise that might be suppressing that relationship. Because remember I said last week that when we have error or noise in our data, it almost always, with 2 variables, it always suppresses the relationship. With more than 2 variables, it's a little bit more unpredictable, but generally it would suppress. And so if we had a small relationship and we really thought we could, if we had a larger effect size, we'd have more power. There just isn't a whole lot we can do. We probably did about everything we could to find that small effect size. I assume that you carefully designed your questionnaires and carefully crafted your experimental manipulations, and you did all of those things that you could do. And so there's probably not a whole lot that one could do there. But then finally, we get to sample size. As n increases, statistical estimates become more precise. Right? If you think about the standard error of the mean, which is standard deviation divided by the square root of n, and not that you need to know that formula for this class, but it gets smaller as a function of the square root of n, and so as n goes up, your standard error goes down, and we're being more precise, and so having said that, the power of the statistical test also increases with a greater n, again, all else equal. And I suspect that I have a graph that looks familiar. Here we have the same test that we're doing. In this case, we're holding everything constant with the exception of n. And if we have n equals 50, our power is about 0.1. And then we get pretty good return on adding additional sample, increasing our sample size. But at some point there's some diminishing returns there, right? And as we if we blew this out larger, this line, because we're almost to 1 here, there's not a whole lot of upside, but it's going to continue to get closer. But we sort of, if you were going to do a cost-benefit analysis, which we could do, our cost would probably outweigh our benefit somewhere before we got to, I don't know. It seems to me for sure before we got to 1,000, and maybe even before we got to 750. We'd have to think that calculation we could do if we wanted to. So does that make sense? And so we think about questions. Make sense? Good. If we think about types of power analysis, the only one that seems to make sense to me is this a priori power analysis. If we do power analysis post hoc, so we calculate what was the power of your test given some alpha, some effect size, and some n. If your alpha is not significant, guess what? Your power is going to be low. If your alpha that you get for your test is 0.001, guess what? Your post hoc power is going to be greater than, it's probably going to be pretty close to 1. It might even round to 1 in SPSS. So SPSS has, for many of the different functions we'll use it for, it has a little thing that says power or power analysis. I forget what it says, but it has the word power in it for sure. But it's this kind of power analysis, nearly useless. Not a kind of a power analysis that will be as important, because there really isn't, at that point there's not a whole lot you can do. You're not going to change alpha, you can't change your effect size, and I guess you could go and collect additional n if that's what you thought you needed to do, but that probably would be difficult, if not impossible in some cases, and maybe complicate your study more than it helps. So that's one kind of power analysis. Another kind, and the one that's we'll talk about in this class, is what sample size do I need given some effect size and some alpha and some power, right? How large of a sample do I need? And so two of the three we've already said are fixed, right? Alpha is fixed at 0.05, right? May as well just go with that. Power is fixed at 0.8 is almost always what people use. You might find somebody that maybe they're doing some study that they just think that for this study it needs to be lowered or raised, and they're going to make that argument. Just like somebody can make the argument that this is a new area that we're doing research in, and so we need the latitude to be able to have alpha at 0.25 or 0.15, whatever. They can make that argument, but for our purposes, and I think in most research contexts, you'll be perfectly fine setting alpha at 0.05, setting power at 0.8. Nobody will argue with that at all, because they're very it's almost received wisdom, right? It's almost it's just that's the way that we've done it. And so what we have then is the effect size, right? We have to come up with, well, what is the effect size? Not always easy, not always a precise point that we know with a lot of certainty. But we can approach it in a couple different ways. Maybe there's another study that somebody else did that is using similar set of variables, maybe slightly different. Maybe you could rely on that study. Maybe somebody has done a meta-analysis, which is a study that takes a large group of studies in one particular area and calculates, well, what's the average effect size, and what are the things that would moderate that effect size, and you could look to see, well, what effect size do they report for the phenomena that you're interested in, or the theory that you're interested in. That would be probably a a decent number to start with. Another number to start with would be, well, how about small, medium, large, right? I just think this I think this relationship is small. Well, we have an idea of what small is, right? Well, I think this is medium. Well, I think this is large. And so, absent all other information, that would be probably a reasonable approach, right? Well, I think this relationship is small. And then you'd have to make some argument as to why you think it's small and convince your colleagues that you're right in that way. Or it's medium, or it's large. And then you plug in what that effect size would be, and then we get, well, how large of a sample do I need to collect for my study? Does it make sense? And this is why we do power analysis, is so we can determine how large of a sample do I need to collect. If you're going to do a National Science Foundation grant, they require that you have a power analysis. I don't know that every quantitative advisor here requires, in a dissertation perspective, that the student include some kind of power analysis. If I'm on your committee, I would ask you to do that, and it's not all that complicated, but it's never perfect, right? If the power calculation says you need 81 participants, that's better than just guessing or just getting whatever you can get, but 81, there'd be sort of margins that you could put around that. Well, if I'm somewhere between 75 and 100, that's probably a good place to be. And so it's never, even though when we do the power analysis, we get an exact number, but they shouldn't be viewed as, I need exactly that number, because we don't know exactly what this is for your study. And so if I was going to make an error, I would err on the side of underestimating what this is going to be, right? So if you overestimate, you're going to probably collect a smaller n, and then you might make a type 2 error. If you underestimate, you might have to spend more resources to collect your sample, or take a little more time to collect your sample, but it probably would pay dividends. So just some advice there. Another way, we could also calculate power as a function. We could calculate, we need this particular effect size in order to have this alpha, that and some power. And again, we don't have much control. We have limited control over effect size. So it's sort of, it's not a particularly good place to start. Likewise, we have limited control over what we can do with alpha, and so it's probably not the best place for us to start. And so when we use the G-Power program, all 4 of these are in there, but the only one that makes sense to me, at least for our purposes in this class, would be a priori power. So the most practical use, I beat that horse. Too little power and the effect may be missed. Too much power, right? Can you have too much power? Potentially, and the wasted time, effort, resources, money, again, put into collecting the data when you don't need that. And then the other potential downside of having too much power is detecting effect sizes that are so small. So Cohen says small is what? 0.01. So what if we find an effect size of 0.0001? That's a lot smaller than small, right? And so is that effect size so small as to have no practical significance? It may or may not, depending on the context. It may or may not. But some would certainly argue that there would be some point where finding, if we had unlimited resources, we could have sample sizes that are a billion rows of data, and we can detect effect sizes that are, you know, 10 to the minus 9. So what? I mean, it really doesn't have any, it likely has at best limited practical significance and probably in practice no practical significance. So some would say that we can, some would say that we can have too much power. If you want to strike up an argument with your colleague, just bring that up sometime, especially a quantitative researcher, because most quantitative researchers sort of have an idea, and I'm one that thinks we can. Others think it's just not, you're stupid. You can't have too much power, and I just disagree with that, and so it's interesting debate material if you like debating statistical things with your colleagues or with other faculty. So some methods to increase power use larger sample sizes or use larger samples. We can improve the reliability of our measure, which will increase our effect sizes, and so that might be an avenue one could take. It might be, and I've worked a lot over the years with Claude Miller. This is a big thing. This is something that Claude talks about. Just make sure your manipulation is strong, and just make it really strong. So don't just have it be fear appeal, but have it be fear appeal where they have an accident on themselves when they're watching a video or whatever, right? Just have it be, just amplify that in a way. And I've worked with Claude long enough that I've seen him. You know, he'll think about a student will have particular manipulation, and he'll think of a way to sort of put that on steroids or to amplify that in a way. And that's as long as it doesn't become, as long as there's not diminishing returns in doing that, it probably makes a lot of sense. If we do repeated measures or within participant designs, we tend to have less error. So if the same people can be the control condition and the experimental condition, that would be a within participant design or repeated measures. We have less error because we're dealing with the same people in both conditions. So it can happen, or it can work with some designs. Other designs, it becomes more complicated, and we just can't do within because we might key them off to what we're studying, and that would have consequences for us. And so I want to talk a little bit about the Cohen article. I want to talk a little bit about the Cohen article and then the G-Power program. And then I've already said my piece about SPSS and power analysis. So here are 4 problems. And we're going to work through these 4 problems with both the Cohen article and with G-Power. And you'll quickly see that why would you ever use the Cohen article if you have G-Power? And there's no good reason why, other than maybe your computer broke down and you need to make a calculation. But there's not a good reason to use the Cohen article. But I just want to show you that they're one and the same for the most part. And I think there's some value in sort of working through what Cohen, the charts that he gives us. And so our first problem is we want to know what is the approximate N needed for a multiple regression analysis. And if you don't quite remember what multiple regression analysis is, it doesn't matter at this point. But what is the approximate N needed for a multiple regression analysis where we have 7 independent variables? Alpha is set at 0.05. Our anticipated R squared is 0.2. Is that small, medium, or large? Yeah, closer to large than me, right? But it's somewhere between medium and large, right? So good, good. And then we set power at 0.8. So we'll start with the Cohen article, and I'm going to turn some lights on for those of you that might benefit from that, like me. So Cohen article, print it out or on your computer. two tables that we care about, table 1 and table 2. And so in most cases, you have to use both table 1 and table 2. I think a couple things that if you haven't highlighted them in your article, let's highlight them now. On page 156, under sample size, he says for statistical tests involving 2 or more groups, n as here defined is the necessary sample size for each group. Right? So if we have 2 groups, we have to take it times 2. If we have 4 groups, we have to take it times 4. Right? So it is if we're dealing with groups in this article, using this, we have to, it's just the n per group. When we do G power, it gives us total n. So you just have to remember to make that change. He does talk about under method and the significance, or what does he talk about it? Under effect sizes is where he spends some time talking about his small, medium, and large, and so if we look at table 1, and what he asks us to do is to first convert into some particular effect size that he uses, and so we have to take some data in most cases and do some calculation, and then we determine is the effect size small, medium, or large, and then we take that information and we flip over to table 2. We're always going to be dealing with the middle 3 columns where alpha is 0.05, and we insert our small, medium, and large, and we reference the right test, and it gives us excuse me, it gives us an approximation. It gives us an n for that particular effect size, small, medium, and large. So let's do our what's the problem again? We're doing multiple regression. So we're going to be using number 8 on table 1. Multiple and multiple partial correlation. It doesn't say the word regression in there. We just have to know that that is regression. And our effect size is our anticipated R squared is 0.2. And he says that we need to calculate this thing that he calls F squared. I think that's an F. It looks like an F to me. And we calculate F squared by taking R squared over 1 minus R squared. So that would be 0.2 divided by 0.8. And your calculator would tell you that that's 0.25, right? And is 0.25 small, medium, or large? Given his metric, right? Somewhere between medium and large. Is it right in between medium and large? Yeah, so it's smack in the middle between medium and large. And so we have to just remember that fact. How many independent variables? 7. So now we're going to flip the page and we're going to go to 8. Again, multiple R. 7 independent variables. Alpha is equal to 0.05. If our effect size was medium, what would we need? How many? N equals what? 102. If it was large, we'd need 48. So we're somewhere between 102 and 48. Not particular. I mean, is it useful? It's okay. It's better than having no idea. But at least you have a min and a max. The thing that you can't do, and the reason you can't extrapolate. Well, let's just take the point mid between, because our 0.25 was mid between 0.15 and 0.35. We can't take the midpoint because the extrapolation isn't linear, because it looks nonlinear, and so it would always be, it would be sort of dangerous to say, well, I'll just take the midpoint between those. The best we can do with this, given that problem, is the best answer would simply be the n that you need is going to be somewhere between it's going to be somewhere between 102 and 48. Right? Everybody buy that? Um, so far, so good. I could give you more of those problems, and you could solve those. The other way that we can do it, and again, when you have G power, or those of you that use R statistics, there's a package in R called PWR, and it just takes the same arguments that we use here, pass it a alpha, pass it an effect size, pass it a few other pieces of information, number of independent variables, and it's going to give you what your sample size should be. So, but we are not going to use R in this class. We are going to use this program called G Power. And so this is free, and you get what you pay for, right? And so it doesn't let me change the size of the window. And so I don't know how big of a problem this is going to be. We'll see. I can't make it any higher. I can't make it any lower. I don't know. I don't even know what's below there. There's a few things below there, and from using this in other classes, sometimes you'll have it up on your computer, and you can sort of help me work through the things that I can't see here, and I can always change the resolution of my monitor. I'm matching the resolution of that. So we want to use G power to solve that same problem. And the first thing that we need to do is to determine the test family. And this is just something that you'll see this when we start working with multiple regression, that we get an F test. And we test whether our R squared varies significantly from 0 with an F test. And so you'll see that at some point, but right now, why I'm picking F might not be particularly clear to you, but it'll become clearer as we move forward. But just know for regression, it's an F test. And then if we scroll down our different options, there's a whole bunch of them, but there's one that says multiple linear regression, deviation from 0, and then there's an R square increase. You almost always are going to want the deviation from 0, because you want to know whether your R square varies significantly from 0. In most cases, in some small minority of cases, you might want to know whether your R square varies significantly from 0.1. And then you would do the other test. That would be rare and something that I don't know that I've never done an analysis where I was thinking in that way. So it's probably not something that you'll run across with much frequency for sure. So we're going to do R squared, deviation from 0. And then what kind of power do we want to use? Do we want to do a priori? Do we want to do post hoc, compromise, criterion, sensitivity? Which one did I say we? A priori, right? So always make sure it's there. And then it's asking for some inputs here. Does anybody have this up on their screen? Mm-hmm. What input is below number of predictors? Is there anything? No. That's the last one. So you're near the bottom of the screen. Again, I can't resize this, or I'm not smart enough to figure out how to resize it. So we're just going to work with this. And so now we have F squared, same number that we looked at earlier. But let's say we forgot Cohen's formula, which is, what was the formula again? Yeah, let's say we forgot that formula, which surely you will. We could use this little window here that says determine. And the determinant is going to be different, just like Cohen's formula on table 1 is different for all of the different tests. We're going to do the determine. It's saying give me the squared multiple correlation. In this case, it's not R, it's the Greek letter rho, which is the population R square. Well, we don't know what the population R square is, so the best we can do is the sample R square, which is what we're going to use. And what did I say R square was for our test? 0.2? 0.2. And it should give us an F of what? 0.25, right? See, now the thing I can't do is I can't go, because there's a little button down here, right? There's a button down there that says calculate, and I can't get to it. But if you press calculate, what does it give you?
0.25.
Thank you. So I'm not going to make it calculate. I'm just going to go over here and input the 0.25. And then I'm going to say my alpha is 0.05. That's right, right? For whatever reason, G power defaults to 0.95 for power. So all of the problems that I give you will be 0.8. So you'll have to make sure you change that, or you will miscalculate the sample size. And 7 predictors, right? And then if I press enter, instead of and so I get, what do you get below this? So I get 57, and then that's not the total n needed.
Total sample size is 65.
65, was that between our high and low? Well, our high was 102.
Low is 48.
48, so we're in that neighborhood, right? We're in between that range for sure. That makes some sense? For the problems that I have you work in this class, we'll talk about this graph. It looks like it might be useful. I've never found it to be particularly useful. But I'll explain to you what it's trying to tell us, and then you can make that determination for yourself whether you think it's useful. But this is the output that it gives us. And so for example, on homework number 1 that you're going to do next week, or I'm going to give you next week, I'll have you do some power analysis. And I ask you to give me the protocol of the power analysis. And that's obviously what it says up there. And so I just want you to copy and paste this into whatever word processor that you're using. Okay, does that make sense? Other questions on our power analysis that we did? So the graph is really impressive, and I feel a need to explain it to you, even though I don't use it for a diagnostic. I don't use it, but it does sort of look cool, and so I should explain it to you, I think, and then you can, like I said, make that determination for yourself. So under the red curve is you reject the null hypothesis. Under the blue curve, you fail to reject the null, right? And then you can think of these curves, and these are called probability density curves, and these are probabilities on the y-axis. And if we sort of look at this space in here, like this space that's not a part of the red, if we look at this space here, where if we do reject the null hypothesis, and if we were to, well, how much space is this? And that amount of space, we could calculate that. If you ever had calculus, you could just integrate that, and you could it'd be difficult. Well, it wouldn't be that difficult. You could do that easily enough, or we could just do we could do 100 little rectangles, and then for each one of those rectangles might be like 1/100th of that space, and we see how high that rectangle goes, and we could somehow then calculate the same thing. But essentially, the area under the curve that is not red would be our likelihood of making the right decision, or making the right conclusion. We made the right conclusion in the test, and then this is the likelihood that we would make an error, And so the area under the curve, I guess, isn't the conclusion of our. It's not the conclusion of our study. It's the other thing. It's what's true in the population. I think that's the way that we should think about that. The area under the red curve, and the same way with the area under the blue curve. And so you could sort of use that as a way to sort of think about. I need to get an F of 2.175 in order for it to be significant, and if it's below that, There's some likelihood, and if it's above that, there's some additional likelihood. Again, probably useful for some people that might work with power in a way that's different than I work with it. But when I work with power, I just care about, well, about what size of sample do I need to accomplish what I want to accomplish. And in our case, what did we say, 60, 67?
65.
65. And so if I were doing this study, would I go out and collect exactly 65 and not one more and not one less? Probably not. But it just can be do I need 500? No, probably not. Would 40 be good enough for me? Probably not, right? So it sort of helps you calibrate how large should my sample be, and if you're in that ballpark, you're going to be just fine in terms of being able to capture an effect if one still exists. Questions about problem 1? What's problem 2? Problem 2 is saying what total N is needed for 4-group ANOVA, power 0.8, effect size large. That's easy, right? Alpha 0.05. We can do Cohen's. We can get Cohen's article done before we're done today. So the N needed for a 4-group, is that a one-way ANOVA? What's the difference between a one-way and a two-way ANOVA? What is it? What does that mean? One-way means what? Two-way means what? Anybody?
One is a directional hypothesis, one is a non-directional?
Maybe, but I don't think so. It's the number of independent variables you have, right? If I have a one-way ANOVA, does somebody have that? If I have a one-way ANOVA, I have one independent variable, right? The two-way ANOVA, you have 2 independent variables. 3-way, less common. 4-way, I don't know that you ever see them. You might have some control variables, but they wouldn't be factors. That would be part of them. And so in this case, we're doing one-way ANOVA, which is number 7, right? We don't need to use his little formula there. We'll use his formula for problem 4 when we get back next week. We just need to know that we're large, right? The effect size is large. And we have 4 groups, right? And so we flip the page to table 2. 4 groups, alpha 0.05. We get 18. 18 times 4 is about 72, right? So we need an N of about 72. Make sense? And then we'll use G power next Wednesday to do the same, okay? So questions? Comments? Cries of disbelief? I look forward to seeing you next week. I look forward, even more forward, to seeing those of you that we've not talked about your data yet in the next, before next month. We have all day Monday to get it done. I don't know what my calendar looks like Monday. I know Friday morning looks really good so far. If so, look at my calendar, you might be able to get on Friday. Monday sometimes can be touch and go, so I wouldn't wait till Monday to try to get a meeting with me Monday, because there might not be any time that I'll be able to fit. So I'll see you, if not before, next Wednesday. Stop the recording. Thank you. Bonus points.
Yeah. Gold star.
Gold stars, yeah. Goofy professor that can't remember to shut off the recorder.